appears to be right about 9:15, so we will go ahead and get started. So hello everybody, thank you very much for being here with us this morning. We represent Stratus Business Jets, and we'll be presenting to you today a review of our conceptual and preliminary design phases for our two aircraft, the Aria-1000 and the Aria-2000. So you can see in this picture here, we have the larger 8-passenger Aria-1000 in the background, and in the foreground we have the black, smaller 6-passenger jet, the Aria-2000. So here we have our team. We have Mohammed Al-Jahaldi, who is in charge of the landing gear. My name is August Gearing. I was the project manager for this. We have Blaze Golden, who is our chief engineer. Cody Johnson, who is in charge of stability and control. Gomhee Kim, who tracked our weight and balance and center of gravity. Ian Lai, who is in charge of the systems and crew stations. Sho Oguyama, who is in charge of performance. Johnny Perry, who was co-lead of our structures team as well as on our editorial staff. We have Tatiana Toriani, who is the other co-lead for structures and in charge of propulsion. And finally, we have Kyle Wimmer, who is in charge of aerodynamics. So here we have an organizational chart for Stratus Business Jets. It just shows the relations of the IPTs as well as the lead for each corresponding team. So Stratus Business Jets elected to participate in an American Institute of Aeronautics and Astronautics, or AIAA, undergraduate team aircraft design competition for the 2016-2017 academic year. This competition provided an RFP that called for a high-performance family of light business jets. So the two jets in this family are designed to carry 6 and 8 passengers, and they must meet FAR Part 23 and Part 25 respectively. Now, a key requirement for these two jets is that they must share 70% of their weight of structures and systems, excluding the engines. So in addition to short takeoff and landing field requirements, the Stratus jets, the primary objective is to provide comfortable, high-speed, long-range cruise. Range requirement of 2,500 nautical miles and a maximum cruise Mach number of 0.85 will allow customers to make the coast-to-coast journey in a reduced amount of time. As you can see by viewing the range map on the right side of the slide, even when departing from one extreme corner of the country, the range requirement is still enough to make any other location in one a non-stop flight. So here we have just a brief mission diagram for a typical flight profile of the Aria-1000 and 2000. You can see there are a few performance numbers presented there as well. As I said on the last slide, the primary objective of the Stratus jets is to provide high-speed, long-range cruise. And at our long-range cruise speed of Mach 0.77, it's projected to take just about 5.5 hours to complete the coast-to-coast journey. So with that, I'm going to hand it off to our chief engineer, Blaze Golden, to talk about our design approach.
Thank you, August. So, as he said, I'm just going to give you a brief summary of our conceptual design approach. Start off here with the constraint analysis for our 8-passenger Aria-1000. As you can see, we drove our design point down and to the right. By doing so, we maximized our wing loading and minimized our planned form area of our wing, also driving down our thrust-to-weight ratio so we do not have unnecessary thrust and are minimally compliant. This leaves us with a thrust-to-weight ratio of about 0.4, wing loading of 66 pounds per square foot, thrust available of 8,800 pounds, and our max takeoff weight is 21,400 pounds, leaving us with a wing area of about 326 square feet. Similarly, for the Aria-2000, our 6-passenger, again, the design point was driven down to the right. Thrust-to-weight ratio is a bit more here at 0.44. Our wing loading has dropped down slightly to 59 pounds per square feet. The thrust available is now 8,200 pounds due to the decrease in weight, which is now 18,700 pounds. Our planned form area for the smaller jet is 318 square feet, which is only 8 square feet smaller than the larger one. So for our initial sizing, we started off with Roscom's Part 1. From this, we were able to output our fuel weight, empty weight, and max takeoff weight. Between these outputs and our constraint analysis, which was previously shown, we were able to come up with a planform area for our wing and the thrust required to meet our mission requirements. So for our conceptual approach, above all else, was to be minimally compliant with the requirements set forth in our RFP. This includes the FAR Part 23 and Part 25, which was previously mentioned. We went ahead here with an inside-out approach, beginning with our cabin layout. As you can see, that is the cabin layout for the 8-passenger Aria-1000. We elected to have 2 seats facing forward and 2 backwards to package our passengers in the most efficient way. That is also a cross-section of our cabin with a 5.5-foot overall height, including the step, and 5 3/4 width. This was determined based on comparable aircraft and also size to feel after our team visited Textron Aviation Service Center. So some of our most marketable features are our long-range capability, as previously said. We hit 2,500 nautical miles, which sets us apart from our competitors by about 20%. We're also able to cruise at Mach 0.85, which lets our customers get to any destination they wish in a quicker manner. We have a large baggage area, as you can see. It can fit several golf bags and suitcases. There's about 100 cubic feet in the tail cone, as you can see there. We also have several windows and 2 skylights, which are not visible in this image, and those allow a lot of natural light for our customers. Lastly, we are capable of short field takeoff and landing, giving our customers access to a much larger number of airports. So these are the final sketches for our 2 aircraft, the 8-passenger Aria-1000 on the left and the 6-passenger Aria-2000 on the right. 3 main dimensions being shown here are just our overall length, wingspan, and height. You can see the height is the same for the 2 due to the commonality between the empennage and the landing gear. The wingspan is about 4 feet shorter, as well as the overall length being 4 feet shorter due to the decrease in cabin length. So next up is Kyle Wimmer. He will be talking about aerodynamics.
All right, thanks, Blaze. So the first decision we had to make was what airfoil we were going to be using. We decided to go with a NACA 6 Series laminar flow airfoil, specifically the 63210. This is a 10% thick airfoil with a 1% camber. This allowed us to reach a critical Mach number of about 0.74 with this airfoil. Once we had the airfoil selected, we then began wing design. Knowing our reference or our planform area from the constraint analysis, we were able to begin sizing the wing. As you can see here with the Aria 1000 and 2000, they are slightly shorter in wingspan. We just clipped the tips a little bit to adjust for the wing loading for the Aria 2000. This yielded us an aspect ratio for the 1000 of about 7.75 and about 6.9, with a E of 6.8 for the Aria 1000 and 6.9 for the Aria 2000. Once we knew our cruise weight, we were able to calculate the lift needed and solve for the incidence angle of the wing. This helped to minimize our trim drag throughout our cruise phase. We did sweep the wings approximately 29 degrees, and this allowed an increase in our critical Mach number from 0.74, as I previously mentioned, to almost 0.77. Once we had the wing, we were able to adjust the 2D lift curve slope for the airfoil to a 3D for the wing. This yielded us a CL max of 1.25 at a takeoff condition with 15 degrees of flaps, at cruise 1.0, and at landing with 35 degrees of flaps, 1.53. Our required CLs for takeoff and landing are below the maximum, allowing us to stay out of the stall region. Similarly, for the Aria 2000, the 2D CL alpha was adjusted. The values are slightly higher on the max. This is due to the increase in the Oswald's efficiency previously stated. When sizing our flaps, we first looked at comparable aircraft and then adjusted for what we needed specifically for ours. As you can see, we fall nicely into comparable aircraft with about 20% of our chord being used for flaps, as well as around 50% of our wingspan. Once we had the outer mold line of the aircraft, we used the coefficient of the skin friction method to estimate our CD0 for the total aircraft. Again, we're nested nicely in between some comparable aircraft. Though the CFE method is fairly accurate for a first estimation, we did go more in depth, calculating the CD0 for each component and summing them all up. This allowed us to take into account transonic wave drag once we hit our critical Mach number. The table on the side shows all of the CD0 values for various phases of flight, as well as the figure which shows where our transonic wave drag kicks in. Once we hit our critical Mach number of around 0.76-ish, we start to get a slight increase due to the transonic wave drag. That increase spikes once we hit our drag divergence Mach number between 0.85 and 0.9. Once we had the aircraft total CD0, we were then able to calculate the aircraft total CD and create our drag polar plots, which you can see here. At our long-range cruise condition of 0.77, our best L over D is about 14, and at our max speed of 0.85, we're just under 14. Similar method was done for the Aria 2000. However, due to a slight increase in the CD0 values for the Aria 2000, the maximum L over Ds did decrease to around 13.5 and 13 respectively. We also plotted our max L over D versus Mach number for endurance. As you can see, at 35,000 feet, we'd want to cruise about 0.55, and at 40,000 feet, about 0.7. Ideally, though, our long-range cruise will be higher at 0.77, so our L over D will be slightly lower. And the same was for the Aria 2000. Again, due to the increase in CD0, the L over, or the maximum Mach number for the best L over D did decrease slightly. Since our aircraft is cruising at a high Mach number, we looked at a Sears hack of the aircraft. The dashed blue line is of an ideal aircraft, and as you can see, we're far from it. And this is due to the nature of business jets, the placement of the wing and engines, creating the double bump, which you see here. This is just the price that we have to pay for this type of configuration. The fairing, though, does do a nice job of smoothing the transition between the fuselage and the wing, which is one of its main purposes. The same was for the Aria 2000, with a slight increase in the nacelle and pylon due to a longer nacelle for a longer engine, as well as a little larger diameter. Next, I'll pass it off to Sho for performance.
My name is Sho, and I'll be introducing performance of our aircraft. Thrust available and thrust required for these two aircraft were calculated using the density ratio and the TSFC ratio according to each altitude of the aircraft. For Aria 1000, we have an initial rate of climb of 5,000 feet per minute, which is the right after the takeoff up to right after that. And max rate of climb at the 35,000 feet altitude, which is the cruise altitude, we have 2,200 feet per minute, which is shown in the blue lines. And at the service ceiling, we have 700 feet per minute. For the service ceiling, we are required to have just 100 feet per minute, which is exceeded very well, which is shown in the green lines as well. For Aria 2000, we have an initial rate of climb of 5,100 feet per minute, and at 35,000 feet, which is the cruise altitude, we have 2,200 feet per minute, and at the max, service ceiling of the aircraft, we have 550 feet per minute, which is shown in a green line, as long as the cruise altitude on the blue line. We get specific excess power envelope. This is also analyzed using density ratio and TSFC ratio according to the altitude. On the right side of the plot, we have anomaly going on. However, this is possibly due to the fact that the aircraft is going at the high end of the subsonic, which makes wave drag going in as well, in which we think that is the case. And this will be further investigated next semester as a detailed design of this course. This is the excess power envelope diagram for the Aria 2000. Our aircraft market points are the range and the payload that we can have for passengers. For the cruise altitude, we have a 2,500 nautical miles range with the 4 passengers, with the 2 pilots under FAR 25, and we have a linear relationship going down with more payload on. Range and speed relationship, we have 2,500 nautical miles at the Mach number of about 0.75. This is without any of the takeoff, landing, either maneuver. It goes down as the speed goes up. However, this is due to the fact that this is business jet going faster, makes it travel quicker, in which that is more or less better. And that is something we decided to go with paying for the drag of the aircraft. We have very similar relationship for the Aria 2000 as well. We have 3 passengers as a long-range cruise condition, along with just 1 pilot under requirement of CFR Part 23. And it goes down up to the 500 pounds of maximum payload with 6 passengers, with 2 pilots, total of 8 persons in the aircraft. We have the same relationship with the range and the speed on the right-hand side of the slide. For the takeoff of our aircraft, we have 3780 feet for the balanced field length, which is under the 4,000 feet requirement for the takeoff process. For the Aria 2000, we have 3,400 feet, which is also under the requirements. We have climb angle of 20 degrees for Aria 1000. Aria 2000 has a 21 degree, and both of the Aria 1000 have a FAR 25 clearance requirement of 50 feet obstacle. On FAR 23 for Aria 2000, we have 35 feet of obstacle clearance, and that is included in the calculation. For landing of our aircraft, we have ground roll 1,840 feet for Aria 1000 and 1,540 feet for Aria 2000. For landing field length, the requirement is 3,600 feet, 2,800 for 1000 and 2,500 feet for 2000. Both of them are well under the maximum required length. This is clearing the 50 feet obstacle coming into the airport. Now we are introduced in proportion. I will hand it to Tatiana.
Thank you, Sho. I'm Tatiana Toriani, and I'll be talking about the propulsion system for both aircraft. The engines chosen were based off of the thrust-to-weight requirements stated by the design point in the constraint analysis. The Honeywell TFE 731-48R was chosen for the Aria 1000, and it is also used on the Gulfstream G150, which is a comparable aircraft. The Pratt & Whitney PW545 was chosen for the Aria 2000, which is also used on the Cessna Citation XLS, another comparable aircraft. As you can see from the table here, the length and overall height of the Pratt & Whitney is a little bit larger or around the same as the Honeywell, even though it produces less thrust, and this is reflected in the nacelle design. The nacelles were optimized for cruise at 35,000 feet at Mach 0.77, and they were also designed to minimize installation losses. As you can see from the tables here, our calculations estimate the losses to be less than 1%. In this graph, you can see TSFC variation with Mach. As you can see, it is a linear relationship. As Mach increases, so does the TFC at each of these key altitudes. The location of the engines was based off of comparable aircraft, as well as making sure that the engines had clean air. This meant that the engines had to be placed at approximately 45% of the overall height of the aircraft, and at approximately 65% of the total weight of the aircraft. The thrust reversing system chosen was the clamshell door system, and this is because it is more modern and effective at redirecting the flow forward. As you can see here, it was used on the Dassault Falcon 200, which is also a comparable aircraft. In this case, the braking power is proportional to the throttle setting, where a maximum of the 60% of the thrust can be redirected forward. Now I'll hand it off to Cody Johnson for stability control.
Good morning, everyone. My name is Cody Johnson, and I'm going to be talking to you about the stability and control for the Aria 1000 and the Aria 2000. So the basic design for our aircraft was to be minimally compliant with the FAR 23 and 25 requirements, as well as meet any other maneuverability requirements and stability requirements. Our design philosophy was such that the empennage would be the same for both aircraft, so we would meet the 70% similarity between our two designs. We went with a T-tail for the elevator and rudder. This would allow the elevator to be out of any possible washout effects due to the engine or the wing. The diagram above shows that even at 9 degrees, which is beyond our necessary rotation angle for takeoff and landing, our elevator still is out of any possible washout effects. The way we designed the sizes of our elevator was we took comparable aircraft and then we iterated from that size until we were in compliance with our requirements. Seen above, you can see our aircraft is a little bit to the left of the cluster, but we're still within normal aircrafts or normal ranges. The reason we're left of the grouping is because we had to have a slightly smaller than nominal surface sizing for the elevator to push our aerodynamic center forward and reduce our static margin. However, we are still able to meet all of our performance and stability requirements. Our elevator can produce a positive nose-up pitching moment for takeoff beyond our rotation angle of 7 degrees with just 28 degrees of deflection for both aircraft. And that's shown in this graph above. To size the rudder, we started similarly with comparable aircraft, and then we iterated through until our aircraft was in compliance with our requirements. We nest pretty closely with all of our comparable aircraft right there in the center. The verification for our rudder sizing were to meet the FAR requirements at 23 and 25. The first of those two requirements is crosswind landing. We had to be able to land with 25 knots of crosswind. We were able to complete this with 33 degrees of deflection for the Aria 1000, and then 33 degrees of deflection for the Aria 2000. The other requirement was we had to be stable with one of the engines out. To do these calculations, we assumed one engine was on maximum thrust, and the other was acting as a flat plate, creating maximum drag. And we were able to compensate for that kind of moment with 9 and 8 degrees of deflection. So we were in compliance with those requirements. We also had to calculate the static stability and damping derivatives. Our static margin for both aircraft is positive for all flight configurations. And our flight configuration static margin shifts 2.6% on the Aria 1000 and 4.8% for the Aria 2000, which minimize trim drag because those are pretty small ranges. All of our static and damping derivatives are also within stable ranges, as you can see in that lower graph. So we do meet all requirements. We are a stable aircraft, and we meet the FAR requirements as well as our other stability requirements. Next, I'm going to hand it over to Gam-hee Kim, who did all of our weight and balance tracking.
Thank you, Cody. My name is Gam-hee Kim. I will talk about weight and balance analysis. By using Roscom's Class 2 method, we are able to estimate component weight of Aria 1000 and Aria 2000. By using them, we have estimated empty weight of about 12,000 pounds for the Aria 1000 and about 11,000 pounds for the Aria 2000. Using previously found empty weight, we add crew weight, fuel weight, trapped fuel and oil weight, and payload weight to get the takeoff weight. The fuel weight was estimated with the given payload weight and number of crew from the RP, and trapped fuel and oil weight was estimated by using Roscom's approximation. By adding them all, we have takeoff weight about 21,400 pounds for the Aria 1000 and 18,700 pounds for the Aria 2000. RFP requires at least 70% of commonality between two aircraft, so we used our CATIA model to check how many structural components can be shared between two aircraft. and we also check the volume to fit the same equipment. By doing that, we have about 62% commonality for the structure and 84% commonality for the fixed equipment. And finally, we have overall commonality between two aircraft is about 71%. We also estimate center of gravity of both aircraft to check both aircraft have gyro stability level during their mission. So this is for the AIAA-1000. The solid line graph represents the maximum payload case, and then dashed line represents the maximum range case. The overall CG range of AIAA-1000 is about 7.5 inch. And this is for the AIAA-2000. Once again, the solid line on the right is for the maximum payload case, and then dashed line is for the maximum range case. And then so dashed line on the left is for the maximum payload case, but with the two pilots. And overall CG range for the AIAA-2000 is about 7.7 inch. And now I will hand over to the Johnny for the structural analysis.
Thanks, Gummy. So today I'm going to be talking about the structures of our aircraft. Above is the structural model for the Aria 1000. So this first slide just talks about some initial estimates for cross sections that you will see for some models in the next couple of slides. So as you can see, our rib is modeled as a C-beam, our spar is modeled as an I-beam, the frames are modeled as T-sections, and the longeron and the keel is modeled as a solid rectangular beam. On this slide are the wing and empennage structural models. As you can see, the front spar is at 15% of the chord, the rear spar is at 75% of the chord, and we do have an additional landing gear spar due to where we had to place our landing gear due to the CG. The four ribs connected to this landing gear will be thickened, and there is also an additional mainframe to account for additional loading that would be placed on the spar during landing. The ribs of the wing are every 24 inches, and this is based off of Roscoe's method. There is a production break in our wing, so you can tell that the ribs are initially parallel to the fuselage and then are perpendicular to the leading edge of the wing. The horizontal tail and vertical tail have a very similar structure, same cross sections on all of their members. The only difference is the spacing due to their smaller size. You can also see that a couple of the tail frames are thickened where the vertical tail is connected to our tail cone. This is various bodies of our aircraft. So along the fuselage, the frames are every 24 inches. Again, that is in accordance with Roscoe's initial estimate methods. There are three main spars that are thickened. Those attached to there are three main frames, that are thickened, and those attached to the spars of our aircraft. There are longerons every 6 inches around the circumference of our fuselage. The spacing in the frame is followed into the nose cone and the longerons and the frames. There is an additional frame in the nose cone to support the windshield in the cockpit. The fairing on the bottom right keel had to be added because we are carrying fuel within our fairing and we had to be crash worthy. The frames are placed every 24 inches, and that is so that they're in accordance with the frames in our fuselage. It should be noted that the fairing actually continues up to the fuselage to have a solid piece and support the whole loading that would be placed on the fairing in case of a belly landing. Here you have the flight envelope of our aircraft. On the left side of the graph, you have our VN diagram at various altitudes, most importantly sea level, 35,000 feet, which is our cruising altitude, and our max ceiling of 45,000 feet. The upper G limit is 2.9, and that is from FAR requirements, and our most negative G limit is negative 1.1. On the right side of the slide, we have the VN diagram at sea level as well as gust loading. The gust loading equations were used by the FAR requirements. Here you have three different estimations we've done on our wing using Schrank's approximation. The lift distribution, you can tell, is very evenly, and it's very similar to an ideal situation. The data in the shear and moment diagrams will be used next semester when we calculate the loading on our wing. And now I'll hand it off to Mohammed to talk about landing gear.
Thank you, Ma'am. Good morning, everyone. My name is Mohammed Al-Jihadi, and I'm going to review the landing gear of the Aria 1000 and the Aria 2000. A tricycle single-wheel configuration has been chosen for its light, weight, and simplicity, which is commonly used by other aircraft that have the same size weight. The nose gear and the main gear are using a hydraulic actuator for extend and retract, and they are using audio pneumatic as a shock absorber with a scissor link to support the suspension system, and equipped with high pressure nitrogen for the emergency scenarios. While the main gear is mounted to the wing, the nose gear is folded under the avionics cockpit. For our weight distribution, the nose gear of the Aria 1000 and Aria 2000 meant to support between 8 and 13 of the total aircraft weight, depending on the flight condition, which is due to the CG shift. However, a minimum requirement of 8% on the nose gear to allow the aircraft to steer on the ground. For our positioning, we have the wheel base, which is the distance between the nose gear and the main gear. And we can see that the Aria 1000 has a much larger wheel base, which is due to the difference in the length. In the wheel track, which is the distance between the two main gear in the back, we can see that there are the Aria 1000 and the Aria 2000 are sharing the same distance, which is due to commonality requirement. For our ground parameters, the tip over angle, which is the angle, which is the lateral rotation angle, we can see the Aria 1000 and the Aria 2000 are meeting the requirement to be less than 65 degrees. For the tip back angle, which is the longitudinal rotation, we can see also that the Aria 1000 and the Aria 2000 are meeting the requirement to be more than 12 degrees. For the tail strike angle, or the maximum angle before the tail hit the ground, we can see that the Aria 1000 and the Aria 2000 has a higher angle than our rotational angle. And now with human factor, again, Leo.
Hello, I'm Ian Lai, and I'll be talking about the human factors in our aircraft. So for our control arrangement, we've decided on the side stick control for the cockpit, or the flight control. This is chosen because it is a more modern design, and it's more intuitive for the pilots. Also opens up the cockpit more, where there's more room in the cockpit. There's a mechanical linkage to the primary flight control surfaces with a hydraulic assist. For the avionics, we have chosen the Garmin G3000. That is installed on most of our comparable aircrafts. We have two primary flight displays on the flight deck and 5 multifunction flight displays. Next, the visibility. As you can see from the side view, the required visibility is 20 degrees up and 15 degrees down. We have exceeded that with 31 degrees up and 16 degrees down. From the top view, you can see our maximum viewing angle is 35 degrees, and with a no obstruction viewing angle of 80 degrees. This is a picture of our cabin interior design. We have the Aria 1000 on the left and Aria 2000 on the right. And towards the front, we have a galley towards the front of the cabin. It is used for food preparation and storage. Our well-equipped laboratory in the back of the cabin, and everything in between that is customizable by the customer. Some key features, though, are the aisle widths are 12 inches across. The seat pitch, which is the distance between one point on the seat to the next point, is 31 inches. The tables are stowable to allow more room in the cabin. It is equipped with Wi-Fi, so the passengers can stay connected during the flight for entertainment purposes or to conduct business. Also, There's plenty of room in the cabin, and it's well lighted with natural lighting from the amount of windows and the skylights. Next, I will talk about the systems on both of our aircrafts. This is a picture of our fuel tank. As you can see here, we have the wing fuel tank. Wing fuel tank, our main tank, most of the fuel is located in the wing. We have the forward fuel bearing tank in front of the wing, and the aft bearing tank behind the wing. The reserve tail tank is located in the tail tank, in the tail section, sorry. The reserve fuel tank will hold the FAA requirements of extra 45 minutes of loitering time, as well, and the NBAA requirements of extra 100 nautical miles of detour. Total, our aircraft, the Aria 1000 will hold about 8,000 pounds of fuel, and the Aria 2000 will hold about 7,500 pounds of fuel. And for the hydraulic systems, the main components of the hydraulic system are located in the tail section. They include the main pump, the backup pump, the reservoir, and the accumulator. They can be easily accessible by the maintenance crew from panels on the side of the tail section. We have piston actuators to actuate the landing gear, the thrust reverser, and the brakes. And rotary actuators, which are connected to screw jacks, will actuate the flaps. The main pumps and the backup pumps can be powered by either the engines or the APU. And if any of the 3 engines fail or if any of the system fail, we have stored nitrogen located next to each of the landing gears, which will apply pressure to the landing gear pistons and it'll extend the landing gear and lock them in place for a safe landing. Next, August Gearing will provide the summary.
Thanks, Ian. So we'll wrap up our presentation today with just a few final notes. So here, the thing to note, we are currently compliant with all of the requirements, both performance as well as commonality that were set forth in the RFP. You can look at this table here. We are a bit over compliant in a few areas, and that's something that we will be looking at in the future semester, reducing that excess capability. So the number one conclusion, as I just said, is we are currently compliant with all of our RFP requirements, and that's both performance characteristics as well as I said, the 70% commonality. So cost projections place the Aria 1000 at about 10.5 million and the Aria 2000 at about 8.5. And this does place them right in the range of comparable aircraft in our size class. However, given the superior performance capabilities, it does represent an exceptional value. So going forward in the future semester, we're going to be examining a few things. First off, the use of a supercritical airfoil. This will help increase our critical Mach number, which is going to help reduce our wave drag, and that will allow us to cruise at higher speeds, as well as reduce the fuel required to complete our transcontinental flight. We'll also be examining the use of smaller, more efficient, less expensive engines. This will again help reduce our fuel, and as I said on the previous slide, going to help cut down on our excess performance capabilities, as well as if we can get the cheaper ones, we can cut down on the sale price of the aircraft. And finally, we will be looking to optimize the size of the tail cone and the empennage. This is going to help us cut down on our trim drag, and again, further reduce the fuel that is required to complete our journey. So before we wrap up today, there is a brochure in the front pocket of your presentation. If you would just take a look through that, there's some key performance and interior arrangement options that are available on our 2 aircraft. So thank you very much. Are there any questions?
We'll start with our guest reviewers. Here.
John, overall, I like the decision building machine. Good luck to you for sure. Right off the bat, I'm just going to work backwards forwards. It's easier that way. So it'd be kind of cool to see at the end a cost comparison to yours versus what you're trying to compete with. And then just like at the end, you can justify saying, well, we are a little bit more expensive if you are, but this is why. And we have better performance here and there. Just a good idea to always have. You're trying to sell it. So that way. I thought the side stick idea was interesting for sure. The joystick is preferred. However, for the pilots that I work with, they hate the side stick because turning out gets really annoying. It's harder to do. So if you want to go with the stick, I would recommend going in between the legs because you can turn equally as easy. So it's just an experience that I just had. They were complaining because we had a mission they had to turn right the whole time. And they just were complaining about that on the radio. So then I might have missed something, but on your tail strike and actual takeoff, you say you need, your tail strike is at 19 degrees, but I think on your takeoff you have 21 degrees required. So am I not reading something right? So if you go to slide.
Yeah, our climb out angle is about 20 degrees.
Okay.
Our rotation angle is 7.
Okay.
So we do have a few extra.
Okay, so maybe on the earlier slides when you were talking about taking on is having the climb, like the actual rotation angle on there as well. Okay, so that's good to go. So that covers that. Also, it would be on your range and payload. You talked about the passengers. It would be good to include what your assumed weight of the passengers are. So I mean, I could figure it out, but it would just be easier if you just quickly look at that.
It's 200 pounds per person and 50 pounds for baggage.
As I assume, it is easier to do that. On slide 16, I thought it was really cool how you overlay both wings. I thought it'd be nice though to have them in 2 different colors so you can quickly see that, it's just easier to read just little things, you know. So I thought it was pretty squared away. Business jets aren't really my background, so it's a little different for me to try to think this way, but I thought it was pretty good. Yeah. Okay.
Overall, I liked that you presented a lot of data. The other thing I didn't like was you presented a lot of data. On some of these, I tend to get lost because we're going back and forth.
Yeah.
The original there. Like I said, you had it, it's all there. Everything is there. But trying to make sense of it, like if I were, I'd like to say I'm an investor. I mean, I own a company anyway, so it's almost like I think you're trying to sell this. On some of these, you kind of need to see, all right, here's the requirements, because you have to repeat them in every slide. Like if you're going to show something, here's the performance, here's the actual requirement, you repeat it again, and then show, here's how we met it. And then at the bottom say, yeah, we met it, and here's the margin on it. I didn't quite get that out of all of these. You kept going back, well, RFP said this, and we met it per this requirement, but it's not stated in here. Because someone we're looking at it and be like, okay, I have to reverse engineer what the heck they did, you know. And it's not a dig on you guys at all. I mean, it's just the way it's presented. I like what you did. I mean, like I said, there's a lot of information to try to digest, and there's a lot of slides. As far as the size taking all that on, I wouldn't be able to play.
I just learned that literally.
I don't know. It's like I was on flight there. There's 16 signal. I like that size stick.
There's just an F-18s there. We had a mission and then a flight for 2 hours and then turned right for an hour and a half. So then you would fall back after a little bit and then roll off.
Correct risk.
Yeah, and then go back to adjustment. So
yeah, and then continue to be nitpicky. You know, back to the thing about percent margins. Like even go back to like the economics design on slide 44. You're showing this, effective area, ineffective area. It's a nice picture, but there's no percentage up there. There's no like, okay, the target percentage is this. This is what we have, so don't worry about it, right? And then back to the thing about trying to find out. I should have folded them the way we did. That would have been more organized. There was when we were showing, the passengers and the pilots and stuff. I noticed that one of them, like 1,000. It doesn't have the same labor. It's like, okay, you got 4 passengers plus 2,000 baggage, but then suddenly you got 3 passengers and a pilot.
That is because the FAR Part 23 only requires a single pilot. So our long-range cruise requirement was 2 passengers and 1 pilot.
Right.
But because we have 6 seats in the back, we can carry 6 passengers and 2 pilots.
So you're going back to the showing I know that means, it's just little bit like that. It just allows the audience to just look at it and say, okay, that's what they're trying to tell me. And it's always like, tell them again, tell them what you told them, tell them again. But overall, good job.
Okay, I'm going to start from the back to the front. Really good job. You guys, you can tell that there's a heavy Crisler influence on this. You're making these things work really hard for you, so I like that. You're learning from one of the best, in my opinion. So, let's see, conclusions and recommendations, last slide, 75. Structural analysis using FEA is recommended for the detail design. You should do some hand calculations at this point. Right? My team has just finished in detail right now, says that they waited too long to do structural analysis. They feel that they should have done structural analysis in pre-lim. And so it's a lesson learned that I'm going to push to you guys, and I'll push it out in my prelim classes.
They did have the lower right based on, they did say which assumption was where they got the lower.
Yeah, they got a VN diagram.
So they could have easily pulled that out and then see what right. And that's a quick calculation. Right.
So you can do, simple calculations on the spars for the wings and also the fuselage, launch runs and things. You mentioned here compliant with all RFP requirements. Remember now, at this point in the design, you have no data to back up that claim. You have predictions, you have simulations, analysis, and things. So at this point, you can't say you're compliant, or at least what you can say is that you're predicted to be compliant using the methods that you've used so far. So make sure that you keep that in mind. Let's see, slide 72. Looking at stored nitrogen provide pressure to deploy the landing gear in case of the system malfunction. Is there any other aircraft that has that? Oh, there are. Okay. So I'm just thinking, if that somehow bleeds down and you're counting on that to deploy your landing gear and save your airplane from a really expensive belly landing, you want to make sure, a fail-safe system, good fail-safe system is one that deploys with springs, weights, and maybe aero loads, so that you just basically let it go and it hangs out and blocks and drops, kind of like when the airplane does that. Look at slide 68. I'm looking at your angles there, the blue lines. I like this depiction because it says, blue lines is where you need to be, the green lines where you are. Excellent visual, but I see a problem in the pilot's view on the right-hand side, the no obstruction viewing angle. He doesn't quite meet the requirement. What's your plan for meeting that requirement? Where are you going to seek a deviation?
For the lateral direction, on both pictures on the right side.
Yeah, I'm talking about the lower right picture. Shows the green line and the pilot on the right side. It doesn't meet the requirement. So the blue line is further out than the green line.
They actually is not a exact number required for lateral direction. It's mainly just for longitudinal direction, or just like showing left side. And since the strata is small enough that you can look over anyway, we figure out that it's something that we can go with. So more or less, we have a total visual angle of 35 degrees, and that is actually more than most of the comps anyway.
So you think it's not a hard requirement, it's pretty soft and...
This is, yes.
Yeah, good.
So it's like, don't put the blue lines in, right?
Maybe that's what you want to do.
Yeah, because it is,
Right.
actually, you show the required blue, but down below, you just throw them in there.
Yeah.
Those, the ones in the center is actually the, due to the strap, so that if you look through the strap, that's...
We understand,
yeah,
but
yeah.
you're implying that that is a requirement. Because over on the left, you show this is required, it's in blue. On the right, you're showing blue again, and we're assuming it's a requirement, but it's not.
Yeah, just
They have to
literally
understand.
something else, or just change the color.
Or just take it out.
Yeah.
Just take it out.
I kind of see what you're trying to show though, is that you have these gaps in visibility. So just change it, or just change the label on that, you eventually be able to solve that whole problem. So.
Let's see, slide 60, VN diagram. Really, really good. I love these. There's so much information here, but there's a couple of pieces that you could actually add to this. And one is calling out your VNE, or V sub D. All right, that's 800 knots, or 800 feet per second. Feet per second? Wait a minute. I don't think airspeed indicators have feet per second on them. I mean, knots. Need that, all right? So I didn't even see that first time around. So V sub D, VNE, and then cruise speed, easy to put on there, and then V sub A, maneuvering speed, also easy to get, corner velocity. So those are easy pickouts to put on there. for more information. If you really, really want to make the slides work even harder for you.
We didn't want that.
Hey, these skylights you talked about, let's go back one slide, 59. This is really cool. I was thinking, wow, now I see one. But it looks like there's a longeron that goes right through it, or do you open it up? Does it fit within the longeron spacing?
There should be, the laundry should be outside, but it might be hard to tell because
Yeah, it might just be
over.
behind.
Okay, all right. So you basically have enough opening in the longeron spacing to put these nice skylights through. That's a really, oh, I see, there they are. Okay, got it. All right. All right, nice feature. I'm a little bit kind of wondering if that's really going to work out. 57, I really like this. Initial estimate for cross-section, you show, you put some thought into what the ribs are going to look like, cross-section, spot frame, mainframe, all that stuff. I love it. You guys have actually put some thought into this. You got it there. Good chart. So let's go to slide 49. Your static stability and damping derivatives. There's this neat little parameter that I learned about the other day. I think it's the CL beta or CN beta ratio.
A ratio?
A ratio of CN over CL or CL over CN that kind of gives you some insight into the dynamic stability. Did you guys work that at all?
I hadn't heard of that parameter yet.
No, okay, all right. Let's see. Rudder sizing validation, slide 48. Great that you did this, but I wasn't sure how you did it. What was the method?
I had used methods outlined in Napolitano and Yekout. For forces, they assumed maximum thrust on one engine with a maximum drag on the other.
Okay.
And then it was just outlined in there. Like you had to get all the C and beta and those kinds of coefficients, and then there's a moment balance.
Okay, all right. I wasn't sure if you used a method like that or if you used actual CFD.
Oh, no, it was a balance.
Got it, okay. All right. Let's see. I'll skip over my positive comment. There's a lot of really good stuff here. Let's see, the cell sizing, slide 39. Tatiana, we got that, right? Your losses due to engine installation, less than 1%. Is there something that supports that? I mean, that seems to be a pretty low number. I'm used to now working with props, right? Can you really realistically expect a less than 1% installation loss?
That's probably an ideal value, but I went through all the calculations with Dr. Elliot Briner from the propulsion department,
Okay.
and he sat with me and confirmed it.
Yep.
And this is what we ended up getting.
Okay.
This neglects some nozzle drag though,
Okay.
so it's not
All right.
100%.
What do other airplanes typically get? Did you do any kind of comparison with real airplanes that exist?
I couldn't find that data.
Oh, okay. All right. Let's see. Covered that one already. Slide 29. So it looks like at 45,000 feet, you have 700 feet per minute rate of climb capacity. So theoretically, your service ceiling is higher than 45,000 feet.
Our service ceiling is about 47,000.
So how do you know that?
We continue our calculations of drag and thrust available at higher altitudes. The reason the 45 is presented is that is the required service ceiling.
Right.
So we're just showing the fact that we do meet that.
Yeah, you've got margins, so that's
Yeah.
pretty cool. So I guess you could go to like the piece of S diagram, slide 31, right? You ought to be able to pick it up from that. All right, let's see what else. Slide 22, you might be able to educate me on something here. So your CD calculation, the formula down there, CD naught plus 0.0604 CL squared, is that really supposed to be a minus 0.0006 CL?
So the K2 term is normally a minus term, so it would be plus a minus. So that's why we indicated it that way.
Okay, all right.
It's the coordinate transformation that moves your minimum drag point away from the zero lift point so that you get a positive lift contribution at your minimum drag.
Okay, all right.
But you simplify it by just using the KCL squared term to
Right.
do all your range and endurance calculations, which you can actually do all those calculations, taking advantage of the camera.
Okay, no, I was looking at the weight drag. The last term, I think, is weight drag, is that right?
No, it's the coordinate transformation that moves that otherwise symmetrical CD
Mhm.
off it. If you had a symmetrical
Right.
situation,
Okay.
it would be centered on
I
the.
got it, okay.
You get an advantage from the camber. You
Adjustment
get
for camber.
useful
Okay.
lift
Got
at
it,
your
got it.
minimum drag.
All right, thanks, that's good. Okay. Oh, slide 12. And I think I'm gonna wrap up my comments here. You've got marketable features listed here, but you don't have any numbers, and numbers on this slide would make this a really powerful marketing slide. If business development or BD was in on this, they'd be going, yeah, okay, my mouth's watering, I'm spitting, I'm really excited here, but tell me some numbers. That's it. One last one here. Let's see, slide 11. Minimal compliance kind of has a negative connotation. Another thing you want to do with business development, engineering, that's great. Yeah, you want to just meet the requirements. You don't want to over-design or overbuild and get it to be too expensive. But a better term might be, say, optimize compliance. All right, so that it doesn't have that negative connotation of, yeah, we just did the bare minimum here. We've really thought about this and we've optimized our compliance, so it's kind of a better positive spin on it. Think about the business side. This guy right here is awesome. From a business, standpoint, I think this is fantastic. I've never seen any class do this, but I like it a lot. This is very, very cool. So, nice job, you guys. You guys have obviously done a lot of work on this. The presentation was really, really well done. And I thought the package looked good too. So, congrats.
Thank you. Thank you.
We'll see you guys again in detail.
We have some other faculty members here. Anything you want to add? Cool.
Two questions. Whose idea was it? Okay, he gets an extra point.
Absolutely.
Yeah. Go to slide 58. May not be an answerable question since I guess you didn't do the actual structural analysis yet. But something jumped out at me when you popped that up. The landing gear support spotter. Is that supported anywhere else other than the back end of a handful of ribs?
We do have an additional mainframe that is connects to the same way that the main spars connect to the mainframe. So
Okay, I feel better now.
It's a fairly common feature on larger jets, not necessarily on the light jets, but larger jets do employ a spark like this.
What was the word I used to describe?
Scary.
For the students who are with us, any questions, comments?
Did you guys, when you designed the interior fuselage, I saw you had a standing height in there of 5'6". Was that designed to a percentile person? Or do you really care? Because you're sitting throughout the flight, obviously, but.
So our comps range anywhere from about, in this class, like 5 feet 2 inches to about 6 feet 2 inches. And like we said, we picked something that we thought was comfortable, and we actually toured several business jets.
Okay.
And a lot of it came from that, as well as putting us around the middle.
Okay, that makes sense. I'm 6'5",
Yeah.
So it would be
cramped, but it's also, you spend the majority of your time sitting.
Right,
That was
right.
part of it.
Okay, so you guys looked at similar aircraft and picked it from there? Okay.
Couple of teachable moments. Go back to the slide Professor Zlick was saying when you left the numbers off. When you leave the numbers off and you say things like good, impressive, that's called an unsupported assertion. And if you're talking to somebody that knows what they're doing, you immediately raise a red flag, put their hand on their wall. just don't. Numbers. They just dispel suspicion. They build confidence. They enhance your credibility. Put the numbers on the slides. Make the slides more
Better yet, a visual.
There are multiple places, we talk about this all the time. Anytime you can put a dimension figure in instead of a tape, that's going to make communication that much better. I believe y'all figured out pretty quickly that the sooner that you start doing CAD for these projects, the better things go. And it shows, we've got, the CAD is very mature, I'm very happy. Where you got a good foundation for next semester, getting the outer mold line to do your wind tunnel model, getting the inner structure pieced out so you can do finite element analysis. YACOPS book, the ratio of C and beta and CL beta, trust me, it's in there. It's look in the index under spiral mode.
Okay.
That's where it'll be. So it's just a simple ratio. It'll help you out. One thing I did not see was you showed the FAR requirement for not washing out things, but there's also a thing in Rostam about departure resistance. And I'm blanking out the tail for that. And I especially want to thank our guest reviewers. Anyways, it means a whole lot to them. If you raise teenagers, they can't hear anything I say. But when somebody